In today's lesson, I'm going to go over applications of integration. It's basically going to be a review of the formulas associated with this topic. So first, let's talk about antiderivatives. The derivative of capital F is the same as lowercase f. The antiderivative of lowercase f is going to be capital F. So this symbol, it represents the integral sign. So this is the indefinite integral of f of x. And that's going to give us the antiderivative of lowercase f, which is capital F. And of course, we need to add the constant of integration, c. Now let's talk about rectilinear motion. We know that the velocity function is the derivative of the position function. The instantaneous acceleration function is the derivative of the velocity function. Likewise, the integral or the antiderivative of the velocity function is going to give you the position function. And the antiderivative or the indefinite integral of the acceleration function will give you the velocity function. By the way, you could find all of these formulas in the formula sheet that I'm going to post in the links below. So now that we talked about indefinite integrals, let's talk about definite integrals. So this right here is an indefinite integral because you don't have the limits of integration. But once you include the limits of integration, the lower limit and the upper limit, you now have a definite integral. The result of a definite integral is a number, a value, a constant. Whereas the result of an indefinite integral is a function, whether in terms of x or in terms of t or something. So this might give you a value like 26 or negative 34, but this will give you a function. So this is a definite integral and this is an indefinite integral. But how can we evaluate indefinite integrals? I take that back. How can we evaluate a definite integral? We know that the indefinite integral of f of x will give us capital F. But to evaluate it, once you get capital F, you need to plug in the upper limit and the lower limit of integration. So this is going to be f of b minus f of a. So that's how you can evaluate definite integrals. First, you need to find the antiderivative, and then you need to plug in the upper limit of integration, and then the lower limit of integration, top minus bottom. Now, let's talk about properties of definite integrals. The definite integral of a to b of f of x dx, this is equal to negative b to a f of x dx. So by switching a and b, the sign will change. The definite integral from a to a, this is going to equal 0 because f of a minus f of a, they will cancel. The definite integral of a constant, where you don't have a variable like x or t, just a number, it's going to be that constant times the difference of the limits of integration. So for example, let's say we have the definite integral from 2 to 5 of negative 8 dx. This is going to be negative 8 times 5 minus 2. So negative 8 times 3, that's negative 24. Now, definite integrals are additive. So if we have the definite integral from a to b of f of x dx, and then plus the definite integral from b to c of f of x dx, this is going to equal the definite integral from a to c, f of x dx. And if you want to understand why that's the case, the first one, this is going to be f of b minus f of a. The second one, this is going to be plus f of c minus f of b. Notice that f of b, they cancel. That one is positive, this one is negative, and we get the remaining result, f of c minus f of a, which is what we have on the right side. Now, let's talk about how we can calculate the area under a curve. The most simplest way to do this is to evaluate the definite integral of the function. Now, sometimes you may not have a function, or other times you may have a function that's difficult to integrate. In either case, you could use a limit process to get the area under the curve. So the value of the definite integral is also equal to the limit as n approaches infinity of the sum from I equal 1 all the way to n of the function f of x of I times delta x. So using a limit process, here's what we're doing. Imagine we have some function f of x, and we want to determine the area on the closed interval a to b. So a is where we start, b is where we end. Now, one way in which we can approximate the area is by breaking it up into rectangles. And we can calculate the area of each rectangle using something called Riemann sums. It could be the left endpoints using the right endpoints, or even the midpoint rule. Delta x is the width of each rectangle, and f of x sub I is the height of the rectangle. So we have height times width. That will give us the area of each rectangle, and once we take the sum of all of them, that will help us to calculate the area under the curve. Now, n is the number of rectangles. So for the example that I have, we have a total of 5 rectangles. So n would be 5. As n becomes larger and larger, the approximation gets closer and closer to the exact answer. So when n becomes infinity, we're going to get an exact answer of the area. But when n is a small number like 4 or 5, it's an approximation. But if you were to use 10 rectangles, your approximation will be better. If you use 20 rectangles, even better. So that's why we have a limit process here. Now, delta x is the width of each rectangle. And to calculate the width, it's the difference between a and b divided by the number of rectangles. Now, in order to use this limit process, by the way, for those of you who want to see examples on it, I'm going to post some links in the description section below where you can see how to use the limit process to calculate the area. Now, in order to use the limit process, you need to be familiar with certain summation formulas that'll make the process a lot easier to calculate. Here's the first one. So the sum from I equal 1 to n of the constant c is just c times n. Now, if you just have I, it's going to be n times n plus 1 over 2. For I squared, it's going to be n times n plus 1 times 2n plus 1 over 6. For I to the third power, it's n plus 1 over 2 squared. And you could find all of these formulas in the formula sheet that I'm going to post in the description section. Now for I to the fourth, it's going to be 6n to the fifth plus 15n to the fourth plus 10n cubed minus n, all divided by 30. And there's another one. I to the 4 and I to the fifth, they're not very common, but it could happen where you may need to use it. For I to the fifth, it's 2n to the 6th plus 6n to the fifth power plus 5n to the fourth power minus n squared over 12. So for those of you who want an example of how to use this, let's say we want to find the sum of I squared from I equal 1 to 5. So this is going to be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. Now if this were to go up to 100, it will take a long time to calculate it. But going up to 5, we can do this mentally. So this is 1 plus 4 plus 9 plus 16 plus 25. So 1 plus 9, that's going to be 10. And then 4 plus 16, that is 20. And 10 plus 20 is 30. 30 plus 25 will give us 55. Now, we could use the formula for I squared. It's n times n plus 1 times 2n plus 1 over 6. So n is 5, so that's 5. 5 plus 1 is 6. 2n plus 1, 2 times 5 is 10 plus 1, that's 11 over 6. 6 will cancel, and we get 5 times 11, which is 55. So as you can see, these formulas are really useful for taking the sum of squared or cubed terms. Now let's talk about some other ways in which we can approximate the area under the curve. So dealing with the topic of Riemann sums, if you want to calculate the area using the left endpoints, so first let me draw a number line. So let's say we want to find the area from A to B, and we want to break it up into, let's say, 4 subintervals. So n is 4. This will be x sub 0, x sub 1, x sub 2, x sub 3, x sub 4. Now sometimes n could be larger, so let's also call this x sub n, and let's call this x sub n minus 1, the second before the last one. So the area used in the left endpoints, so there's 5 points here, but we're only going to use 4 because n is 4. So with the left endpoints, it will be 0, 1, 2, and 3. So a generic equation for the area using the left endpoints will be delta x. That's the width of each rectangle. And then we're going to add the heights of each rectangle. So the first one starting from the left, f of x0 plus f of x1 plus f of x2. And we're going to stop at, in this case it will be f of x3, but in the general case it will be f of x n minus 1. So using the left endpoints, we start from the left. We use all the endpoints except the last one. Now using the right endpoints, you could look at it the other way, as we're starting from the right. We're going to use everything except the one on the left. Or in other words, you start from the second one, you go all the way to the end. So starting from the second point, it's f of x1 plus f of x2 plus f of x3. f of x3 is the same as f of x n minus 1. Well, first I need to put dot 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 to write a general equation. Actually, it's better to write it this way. F of x3, and then the last one will be f of xn. So we're starting with the second point, and we're going to stop at the last point. Now, using the midpoint rule, we want to get the points in the middle. So 0.5, 1.5, 2.5, 3.5. So this is going to be f of x 0.5, and then plus f of x of 1.5, and then f of x 2.5. And we're going to continue the pattern all the way to the last point minus 0.5. So here's the last point, x of n. If you subtract that by 0.5, you'll get this point, which for this example will be 3.5. So that's how you can approximate the area under the curve, or even the value of a definite integral, using Riemann sums with the left endpoint, the right endpoint, and the midpoint. And keep in mind, delta x, just like before, it's b minus a over n. Now, there are some other forms of approximate integration that you may want to be familiar with. This includes the trapezoidal rule and Simpson's rule. So let's start with the trapezoidal rule. T sub n, by the way, the area, which is the definite integral, can be approximated using T sub n, just as it can be approximated with a sub l, a sub r, and a sub m. But for the trapezoidal rule, it's going to be delta x divided by 2 times f of x0 plus 2 times f of x1 plus 2 times f of x2, and then this will continue, and then you have the second to last one, f of x minus 1. It's 2 times the value of that, plus f of x sub n. So notice that the first and the last one has a coefficient of 1. Every other term in the middle has a coefficient of 2. Very similar to the shape of a trapezoid. The first and the last point, they're at the bottom. Let's assign that a value of 1. Every other point in the middle has a value of 2 for the coefficient. So that's the formula for the trapezoidal rule to estimate the area under a curve. Now let's talk about the Simpson's rule. S sub n is equal to delta x over 3 times f of x0 plus 4 times f of x1 plus 2 times f of x2, and then 4 times f of x3, and the pattern is going to alternate between 2 and 4 for the middle terms. Now, the third to last term is going to be 2 f of x n minus 2, and the second to last term is going to be 4 f of x minus 1, and the last term will have no coefficient in front of it. So just like the trapezoidal rule, the first and last term has a coefficient of 1. And then all the terms in the middle will alternate between 4 and 2. So the second and the second to last term will have a value of 4. But the ones in the middle will alternate between 2 and 4. With the trapezoidal rule, all the middle ones have a coefficient of 2. And just like before, delta x is b minus a over n. So that's another way in which you can approximate the area under a curve and also the definite integral, is by using the Simpsons rule. Now let's move on to the fundamental theorem of calculus. In short, FTC, part 1. Now let's say we have some function g of x, and let's define it to be the integral from a to x of the function f of t dt. In that case, g prime is going to be equal to the value of f of x. And here's why. Once we integrate lowercase f, we'll get capital F evaluated from the top integrand minus the bottom one. Now, if we differentiate g of x so we can get g prime of x, we need to take the derivative of the results on the right. The derivative of capital F is lowercase f, and the derivative of a constant is 0. So we can see that g prime of x will equal f of x. So we could say that the derivative of this expression of the integral of a to x f of t dt, that's going to simplify to f of x, which we've shown here. And that's the basic idea behind the fundamental theorem of calculus, part 1. Part 2, you're already familiar with it. It's basically evaluating definite integrals. So the integral of a to b of f of x dx is equal to f of b, capital F of b, minus f of a. That's part 2 of the fundamental theorem of calculus. Now, the next topic is something called the net change theorem. It looks very similar to part 2 of FTC, the fundamental theorem of calculus. The integral of the derivative of capital F is going to be f of b minus f of a. That's the net change theorem. The difference between FTC part 2 is this would be just lowercase f as opposed to derivative of capital F. So the basic idea is if you have some derivative function or some function that describes the rate of something and you want to find the accumulation, you could use the net change theorem to determine how much is accumulated. So let's say if you have a function that describes the rate of water flow into a tank, and you want to calculate the accumulation of water from time A to time B, you could use the net change theorem if you have a function that describes the rate of water flow going into the tank. Same thing with velocity. If you have velocity or how fast something is moving, using the net change theorem, you can determine the displacement of that moving object over time. Now let's move on. I don't want to make this video too long. Let's talk about how we can calculate the area between two curves. So we talked about how to calculate the area underneath one curve, but between two curves, we're going to have two functions. The top function, let's call it f of x. The bottom function, g of x. And we want to find the area between these two curves from A to B. So the area of the shaded region. The area is going to be the definite integral from A to B of the top function, which is f of x, minus the bottom function, g of x. Now sometimes you may need to calculate the area in terms of y as opposed to in terms of x. So let's say we have two functions. The one on the right is f of y. The one on the left is g of y. and we want to integrate it from C to D along the y-axis. So we wanted to determine the area of this shaded region. In this case, the area is going to be the definite integral from C to D of the function on the right, which is f of y, minus the function on the left, in this case that's g of y, dy. So that's how you could determine the area between curves. Now sometimes you need to determine the volume of the shape generated when it's rotated about an axis. So this is going to be the disk method. There's also the washer method, the shell method, and volume by cross sections. But let's start with the disk method. So let's say we have a function that looks like this, and we want to rotate it along about the x-axis, and we want to calculate the volume of the shape generated from A to B. So using the disk method formula, it's going to be pi times the integral from A to B of the radius function squared. So the radius is going to be the difference between the curve and the axis of rotation. Now this can be done in terms of x and in terms of y. So let's say we have a function that looks like this, but this time we want to rotate it about the y-axis instead of the x-axis. And we want to find the volume from C to D. Using the disk method, it's going to be pi integral from C to D, the radius squared, but it's going to be in terms of y instead of x. So ry is going to be the distance between the axis of rotation and the curve. Now I don't want to make this video too long, so for those of you who want the formulas for the washer method, the shell method, and volume by cross sections, in addition to other formulas that I didn't cover in this video, like the work done by a force, the mean value theorem for integrals, average value of a function, arc length, surface area, you can find all those other formulas in the formula sheet, down below this video. Also, I'm going to be posting other videos as well that will give you example problems on how to calculate the volume by the disk method, how to calculate the area between curves, how to use the shell method and the washer method. So I'm going to put a lot of resources in the links down below for those of you who want more practice problems to prepare for your exam coming up. So that's it for this video. Thanks again for watching, and feel free to check out those other videos.